Hi everyone, welcome to my presentation. First, I will start with the overview of the dataset and the objective of this analysis. The dataset consists of 450 observations with 5 predictors, and the variable of interest y represents appliance energy consumption. The main objective was to build a model to predict y using selected predictors and transformations. Over the next slide, I will walk you through the process of understanding the data, transforming it, building predictive models, and interpreting the results. The first task is to understand the data through histogram and scatter plot. For x1, the histogram shows it is positively skewed with a skewness value of 0.94, and x1 also has a positive correlation with y. For x2, humidity in the living room has a distribution close to normal. It is negatively correlated with y. For x3, its distribution seems symmetric with a low skewness of 0.18 and show weaker positive correlation with y. For x4, the variable is approximate to normal distribution but higher skewness of 0.45, and x4 is also positively correlated with y. For x5, pressure is negatively skewed and show negative correlation with y. And for y, the histogram shows it is highly positively skewed with a skewness value of 2.98, which indicates significant asymmetry in the data. Moving on to transforming data, I will evaluate the Spearman correlations between x and y to select appropriate predictors for energy consumption. X1 has the strongest correlation, while X4 shows the weakest correlation, so it contributes very little to predicting Y. Based on this, I will select X1, X2, X3, and X5 for transformation and prediction. Next, I will apply appropriate transformation with the primary goal is to reduce the skewness and standardize data to a unit interval between 0 and 1. For x1, x5, and y, which were highly skewed, I recommend applying a combination of min-max scaling followed by a polynomial transformation. For x2, I recommend applying a negation transformation followed by a min-max scaling because it had a negative correlation with y. For x3, a simple min-max transformation is sufficient and it is already follow a near normal distribution. After transformation, the skewness on variables was significantly reduced, improving their distribution and thus minimizing bias in modeling. Next, I will assess the error matrix and correlation of the 4 aggregation models to identify the best fitting one. As shown in the table, weighted arithmetic mean model was found to be the best with the lowest root mean square error and the highest Bayesian correlation and highest Bayesian correlation. For predicting, I use the weighted arithmetic mean with the transform variables to predict y. The predicted value of y is 58.85 watt-hours compared to the observed value of 60 watt-hour, representing a margin error of 1.9% only. This demonstrates that the one is the best fitting model for this dataset. Also, the calculated weight reflects level of importance for each variable. X1 had the highest weight, making it the most influential predictor. X2 and X3 with moderately high weight, showing moderately significant impacts on Y. Lastly, X3 had the lowest weight, indicating its minimal contribution to predicting Y. Based on the level of importance and relationship with Y, the conditions for achieving low energy consumption are summarized as follows. Lower values for x1, higher value for x2, moderate value for x3, and higher value for x5. While the WAM model performed well with minimal prediction error, it has some implications and limitations. The WAM model is easy to reinterpret and is particularly effective in handling uncertain scenarios. However, its performance depends heavily on the transformations applied to the data, which makes it less effective when dealing with complex datasets.